Sounds good.
All right. Hey, everyone. Okay, so let me open up the roadmap here. Thank you, everyone, for joining our first Manta Tech series. This is going to be the first in many different conversations that we'll be having that are specifically focused around all the developments that are happening over at Manta Network so that the community has a better insight into exactly what we're building, the progress that we're making, and the general technology so that everyone just becomes a little more educated on Manta Network. And so right now we're in the third quarter of 2022. And, we've done a lot of things since that time, right? We launched first we, got a Calamari parachain a while back. And since that time, we've been working very hard on getting things live. We see that, we got the collator program out. We've got the products available on testnet, right? Version 1 and version 2 both launched. And one of the other things that we're trying to get out in Q3, which, we're definitely ahead of schedule here, is on-chain staking. And so as part of on-chain staking, we need to do some consensus changes. And so that's what Adam here has been working on for the past several months. And so today we're here to talk with Adam, or Adam's here to present to us exactly what the changes are, why we're doing this on a consensus level, and what this means for the future of Manta and Calamari Network's technology. And so for anyone who's interested, right, you guys can always check out our roadmap. We update this live. I believe that you can go to mnt.as/roadmap to check that out. And that's what you're seeing on the screen right now. And without further ado, I'll pass the mic off to Adam, who will go into the details about our consensus updates, and then leave the floor for any Q&A.
All right, cool. Thank you, Kenny, for the intro. And also a quick hello from myself to everyone in the community. Thank you guys for joining. Maybe I should start sharing my screen first before I go any further. So let me know, Kenny, if everything looks fine. Maybe can somebody confirm that they see something on screen? Right.
I see your screen.
Okay, awesome. So that said, as Kenny introduced me, hi guys, I've been with Manta, with the project since the beginning of this year. And I'm a developer, so I'm with the backend engineering team at Manta, and we are building what if you are running a collator or a full node, so you are taking part in the blockchain side of our product, then you already have interacted with the Manta binary, which is what we at the backend team are creating for you, my main contribution in the last couple of months and going forward is consensus related work. So we're as Kenny was introducing, we have some interesting bits and pieces on the roadmap that are going to make the Calamari project, we hope, significantly more interesting to everyone. And one of those parts is what I've been working on, which is consensus. And that's what I'm going to talk about to you guys today. So quick list of things. So I'll try to introduce to everyone what is it when I say consensus? What do I mean as a blockchain engineer when I say that? And what is consensus in general? Because it's one of those nice buzzwords like IoT and cloud, where technically everybody has heard of them, but either nobody really knows what the definition is, or everybody has their own definition. So I'm going to present to you guys what my definition or my understanding of consensus. It does not. I'm not an academic, so that this is not a like end all be all thing, but I want to try to get everyone to understand what it is that we're working here behind the scenes for everyone's benefit. So after we've talked about consensus in general, we'll discuss about how it applies to block production in the Manta and Calamari networks. And then I'll do a quick overview of like 3 different popular consensus mechanisms that are being applied in blockchain today. And as some people might have already seen in the roadmap, and also as Kenny introduced, we're transitioning over to the latter one of them, the PoS. So I'll talk a little bit about that. Hopefully we'll have time for Q&A after this. So let me get into the meat of things. First of all, what's a consensus? I could try to explain it to you from the technical side of things. Just talk about it, about what I've been doing in general on the development side. But the problem with that approach is that this consensus topic, when applied to blockchain, becomes like a matryoshka doll, like a stacked puppet of inner layers that we would need to kind of unpack in order for everybody to understand, to get to the understanding of the consensus part. So we'd have to talk about all of these things and make them understandable to get to the concept of consensus. So what I'm trying to do today is to divorce consensus a little bit from the technical side for now, and then later, after we've gone through what a consensus engineer does in general, let's see how it applies to our blockchain in specific. So the way I want to do that is I want to walk you through a hypothetical 3-participant system. So it's a simple example of 3 actors, the only 3 actors for this example, in a system where they each possess some amount of money, some asset. In this case, we'll represent it with US dollars because it's something that probably everybody accepts as an asset. And then these people are just co-inhabiting this network of 3 participants. And everybody is doing some collaboration, some back and forth, some trading maybe, as long as it's consensual, and everything is fine and dandy. Until maybe someday our little participant A here decides that it would be the world would be nicer if he had all the money. So that's something that is probably going to make a lot of people pause for a second. But at this point here, this is not yet for real a disagreement. It's not really a problem at this stage, because when we try to think about how this situation could resolve into the future state of the network. So when we are faced with this situation, what do A, B, and C do in order to resolve this request from A? One completely valid outcome that this could create is the following, where all the participants say, yeah, I don't really need money. I'm happy if you're happy, take my money, and then we'll continue life from there. Right? This is a fairly rare outcome because most real systems don't work that way. But one of the key takeaways here is that what you think is rational behavior is not necessarily also rational behavior for everybody else on the system. Right? So B and C can be perfectly happy with this decision, even when we as an outside observer would be saying, why did you give away your money? Are you stupid? Well, it's everybody's choice in this situation. And here the system resolved this potential of conflict with an outcome that is accepted by A, B, and C. So we have no disagreement. The more realistic situation from here becomes if instead of handing over their money, B and C act realistically and say, I'd rather keep it, thank you. So now we're in a situation where the network is in disagreement. The system is in disagreement. A wants everybody's money, B and C don't want to give A their money. So we have the situation where, how do we resolve it? Either B and C hand over their money and everybody moves on with their lives, or B and C resist in giving their money over. And now we need to so this is also a valid outcome, right? B and C can say, I'm not going to hand it over, and A can then say, I accept that. The system continues moving the way it was before, but in this case, situation, A is unhappy. So if we want to come up with a solution that everybody is at least somewhat happy with, this is the idea of forming consensus. We need to resolve this conflict in a manner that everybody can accept. And in order to do that, what we want to do is we want to form a rule that everybody abides by that resolves this conflict situation. In blockchain space, we call that a fork choice, and a rule that determines which of the potential outcomes of a situation the system is going to choose. We call a fork choice rule. So in this situation now, what fork choice rules could we come up with to resolve this? We already decided two. One is everybody, they hand over their money and everybody's happy. Two is they don't hand over their money, everybody's happy. There are more realistic ones, and now we get into the societal aspect of it, because typically in this situation, if there is something that is it's an imbalance of power. So if A has power over B and C and can take their money against their will, so power can come in in all shapes and forms. It can be economical, can be societal, it can be like social engineering. A can convince B and C to do what he wants them, even though it's not in their original interest. But it can also be plain old violence. That's the most fundamental way of exercising power. And if there is an imbalance of power in the system where one person can exert violence, a valid fork choice rule to resolve this conflict situation is the powerful person gets what they want. That's not. It is a very, unfortunately, very realistic fork choice rule that is being applied in all dictatorships around the world, because it bases on the fact that B and C are happier being alive than keeping their money, and so it's an applied in reality fork choice rule. We can try to improve on this situation though, because when we're trying to come up with a consensus rule, we're trying to make as many participants in the system happy with the outcome of that conflict resolution. Right? In the situation where we have this conflict, we can't make everyone happy. A can't get what they want and be happy, and B and C can't get what they want and make A happy in return, right? So we need to have some way of resolving this. So in order to not get dictatorship, which I hope we can all agree is not the best fork choice rule for organizing society by, we can improve on that, and we get towards like we here in the South in the US call America, which is we try to balance aggression with counter-aggression. And this can actually lead to a more favorable outcome, because now if A has consequences to fear for trying to take people's money against their will and exercising his power, he may be convinced not to do that, right? I mean, as long as A also values his life, he might not want to take stuff against by force against others' will. This is the rule that like nuclear deterrence works by. It's as simple as this, which is kind of mind-blowing thinking about this, but like a lot of actual global politics work by very, very simple rules if you break it down. We can spin this in the situation is actually favorable. It's one of the outcomes of this. There's another valid outcome, which in nuclear deterrent situation would be the same thing on a larger scale, where A doesn't get convinced not to try it, and we've removed participants from our system effectively. Now our 3-participant system has become a 1-participant system, at which point there isn't really much value in the system at all anymore, because while B has now gained a sudden windfall of $40 from the deceased previous members of the system, he's now the only participant of the system. And now he doesn't have anybody to sell his USD to, his asset to. So even though he is now rich in paper money, it's actually in reality worthless. So this is an extreme case, but in general, what this is to say is that if we remove participants from the system, it's always bad, because each system is only as valuable as, or rather, let's put it the other way. A system gets more valuable the more participants it has, right? A city, and also more powerful in return. A city is more powerful than an individual, and a nation state or a state is in turn more powerful than a city because it has more participants, right? So we want to, whenever we resolve conflicts, we want to do it non-violently in a way that prevents people from losing the system, from leaving the system, in that sense. So if we wanted to like not get into that situation, so what can we try to or actually before that? Now, given that we don't want to remove the system, there's one other problem that that's a simple system like this has, and that is the problem of collusion. Now, we have A and C are powerful, B is not. A and C would have to fear getting shot if they tried to do something against one another, but they don't have to fear any consequences if they decide to screw over B. So now we get this problem that A and C are happy and B is not. So how can we think this situation here of power imbalance to its logical conclusion is by rebalancing power. And so the final situation that we end up with is basically the Mexican standoff, where everybody can always exert power over everybody else at any time, and as long as that power is equal. So A, B, and C have equal consequences to fear. In this case, losing their lives if they try to screw somebody over. The system is in a like self-enforcing deadlock. As long as nobody does anything that is going to lead anybody else to pull the trigger, everybody is happy and fine. But if anybody is distracted for just a split second, or let's say A comes up with a slightly better gun than the other two people have that has a slightly longer range, they can devolve this situation back into the very first scenario, where we have A that has one gun, and he just stays out of the range of B and C, and now A is powerful over B and C again. So while this is like an interesting solution that like some people actually do prefer, and like there are valid legal theories about this, this is a like very fragile system is what I'm trying to say here. It really depends on a delicate balance of power to be maintained. So if we don't want everybody to always be afraid for their life at any point in time, how can we improve on this? Now, so typically what societies do is they come up with this thing called centralization of power. So instead of everybody owning guns, now we have one gun that not everybody has access to at any sort of time, at any point in time, but there is like some sort of proxy that decides on when we as the collective are going to use the gun. So in this situation here, now we have only one gun, but we have the situation that A wants to steal money. The fact that we are voting, it's in itself doesn't help us resolve this in any positive, constructive way, because while B is impacted and will probably want to shoot A, C doesn't have to care, and he doesn't even have to act rationally. So in this situation, for example, like C is not impacted by A stealing B's money, so he's going to vote. He can vote anything, literally, and he might even decide to exit the system by pointing the gun at itself if he wants to. Point is, people can act irrationally again. So just plain voting doesn't help us at all. Then there's also another problem. So even if we assume that that people organize outside of the system, So there is like communication between the participants, and now B is trying to convince C to vote to shoot A so that A won't take B's money. There's nothing preventing C from actually saying that he's going to vote for A to make B happy, and then voting something else instead. So we get the problem of like lying on the vote. That is, I think we can also all agree, not necessarily a good outcome for the conflict resolution. And there's another problem that is also very prevalent in reality, unfortunately, which is bribery. The problem that C had nothing to gain or lose from this vote can be simply changed by A deciding to split the spoils of his robbery with C. So now C has some sort of incentive. In this case, it's financial, in order to vote with A and screw B over. So in the outcome of this result is most likely nobody gets shot, right? So we have resolved the situation, but not in a constructive way. So what to do next on this? So we need to improve by creating some sort of framework that we all agree on. Every participant in the system agrees on voluntarily to follow what we call the rules of shooting, and can also be called a law. So this rule simply decides in which situation is this how do you vote in a specific situation, right? That gives everybody a framework to follow and resolve the situation productively, because hopefully somebody at some point has decided that the rules as they are written are a conflict resolution that is in the benefit of the system. That in itself is not granted, but if we look at this, we have a system of laws. Unfortunately, they still are not a good resolution in this case, because the law is badly written. If the law is written in English, it's by nature imprecise, and if somebody wrote a law like this, C would perfectly be following the law in this case by voting to not shoot because it's not his money that was taken. So the next improvement on this is, okay, we're going to amend the law to make it more clear that we're shooting whenever somebody else's money is taken. Now we have a small bonus take on this, because when we make the laws changeable, we run the risk of the lawmakers being corrupted. So in this case, the law was amended with we're going to take other people's money, but because the lawmakers were friendly to A, somehow he managed to get them on his side. They also added this small other fine print to the thing. So even though we thought we can fix this problem by changing the law, in this situation, well, we got screwed. So the lawmakers themselves also need to be how do you say, honest in the and acting in the interest of the system. Otherwise, all of this again falls apart. So now, how do we improve this again? We remove this this fine print that got added, and now we get to this scenario where, yes, okay, we have a law that states we shoot whenever somebody takes anyone's money, but we're not actually forcing anybody to follow the law. We stated so far that the law is following this law is completely voluntary. So if C decides, what do I care? I'm not going to do it, and just stays at home on voting day. There's no consensus reached here in this situation. So nothing will happen. Nobody will get shot, and A can keep the money that he stole. Also not a good outcome of the situation. So I think we're 10 minutes in, and I think I hope it's getting more and more clear that what we're doing here is one of the most fundamental problems of like human society, which is coordination that benefits a system overall. So given that we're in here, I think we're only like about halfway in. So let's continue with this. The next idea is, as we were saying, we're not enforcing anybody to actually go vote at all or vote in the way of that the law states. So in this situation, even though A was convicted to be shot, if there's nobody who can reliably enact this decision that the people made in order to do the shooting, he can just take the gun himself and go back to the dictatorial. I now have the gun and have power over you situation. So we need to introduce a neutral enforcer to the system that is going to actually enact the laws. So in society, a neutral enforcer, at least in theory, and I'm going to stay with the theory at this point, is police. In this case, we can have police do two jobs in order to act on behalf of the system. One is police can enforce the outcome of the vote, and B, police can enforce that people actually go and vote according to the law. Right. So they can impose a fine if in this situation where the law states that A needs to be shot because he's trying to take B's money, if somebody doesn't vote A, police can fine them. That way, we're not removing them from the system, but we're giving them a disincentive, some sort of punishment from staying home and not taking part in the vote and not voting faithfully. So this improves the situation considerably, because now for the first time after 10 minutes, we've actually found a situation where A gets punished for his misbehavior. The system is better than before, but we have still more problems. The first glaring one is instead of just staying home, A can decide to be maliciously compliant with the law and still cut corners and not do the hard work. If we assume that it takes some effort for C to figure out whether A is actually trying to take money from B and A is the culprit. So there needs to be some investigation, and they need to put some effort in it. If I'm C, I can be compliant with the law and still not care about this and save some effort along the way by simply voting everything that doesn't end in shooting me. I'm compliant with the law. I won't be punished by police, and I've saved some effort. The unfortunate consequence of this is that because now we have a majority, because our first law states we do what the majority wants. Now we have 2 votes out of 3 for shooting A and 2 votes out of 3 for shooting B, simply because C decided to skip some effort. And now we got to another very undesirable situation where C is the only survivor of the system. So we need to also prevent this situation somehow. Now, the next problem is what if we have law enforcement, but law enforcement is not actually credibly neutral and always acting on behalf of the law and the system. If somehow A decides and is powerful enough to bring law enforcement on his side, in this case, in order to kind of look away for a second for this vote, he can still go back to the bribery situation and convince C to vote with him, split the spoils, and still evade punishment for this. So bribery is also, in this situation, bribery of law enforcement is a problem. So now we've established that lawmakers have to be credibly neutral, and law enforcers also have to be. So it's getting more and more complicated. What happens in this situation now? If we do have voter apathy while we have law enforcement, it's actually kind of good in the sense that if C is a rational actor and C values his money, he will not do this. He will not vote, right? We've established that, because otherwise police will see that he didn't vote A on this vote and punish him. So we've solved this side of the voter apathy problem. Now, if we assume that that police is actually credibly neutral at this point. We found some magic bullet that's going to make police act correctly in all situations according to the law. We have another problem that is possible very definitely in permissionless systems, but in theory also in real society. And like, there has been enough controversy here stateside in the last election about whether people did this sort of thing. In the blockchain space, when people cast multiple votes, we call that a Sybil attack. And this is a significant problem. One of the hardest problems to solve that's actively being investigated. Where in reality, in real life, if you go to a voting booth, you have typically a government ID that makes sure that you only vote once, even though that also is not perfect, or like seemingly. In blockchain space, in a permissionless system where you don't have any form of ID, you don't have this safeguard. So A can simply cast 3 votes and change the system from being a 2 out of 3 majority into a 3 out of 5 majority, where he himself has the majority vote. He can enact whatever outcome he wants to. So in this situation, he could vote to kill B and C, or he could vote don't. In whatever B and C want doesn't matter. So one part of consensus is trying to come up with ways that prevent this attack from happening. It becomes even more problematic because in this situation, while B and C get shot, A actually lost money because he voted not to shoot A. He voted not to shoot himself, so law enforcement is going to fine him. He has a cost to pay. In this situation, he must have decided that spending $20 by paying the fine to law enforcement is worth the benefit of getting B and C killed. Whether that's productive behavior or rational behavior at all is up to everybody's decision, but people can, the fact of the matter is that people can decide to do it. And it is our role as a consensus engineer to prevent the system from being vulnerable to people doing this, right? Because if we've learned anything from hacks in the blockchain space over the last 10 years, is that if vulnerabilities exist, people will use them. So we need to plug all of these holes as best as we can. This situation becomes even worse if A actually doesn't lose from the situation. So in the previous example, we had a perfect balance where everybody owns $20. Now B and C in this situation are dollar whales, and they own twice as much as A did. So if A steals money from B and C, now suddenly he actually made profit, because even though he had to pay $60 in fine for each of the vote he cast that didn't involve shooting A, he still made $80 in profit, right? So with the $20 he owned in the beginning, he actually has a financial incentive to doing so as well. So finally, after all of this, I think I hope it's become clear to everyone on the call. If not, I can go into more detail in the questions later. What we mean when we say we're trying to design a consensus system, both in general and when applied to blockchain. In general, this problem in its generic form is very hard, and humans have worked on this basically since the beginning of mankind, with all of the iterations of government that we've gone through, and we've been constantly coming up with slightly better fork choice rules, to take the blockchain term, than the previous system had, but we're nowhere near perfect yet. If all of the controversy on the globe is an indication of that. So with that said, let's go to what I would actually say is definition in the broad sense, after hopefully giving you a sense for, even though this was a simple example, for the challenges that designing a consensus is going to face. So I would say a consensus system is a comprehensive, shared, and mutable set of rules to resolve conflicts between participants of a system that can be irrational. So we don't assume that they always act correctly. And a set of rules in itself is valueless if we don't also have a reliable way of enforcing that people adhere to those rules. And this is what consensus is in general. And when we do apply that to a blockchain scenario now, we have this following situation where every blockchain, every single participant of the blockchain. So now, if you substitute that little smiley face here with a node, so put in a computer instead of the smiley face, the gun and the police become the node itself as well. But basically every node, a shared set of rules. And the asset, the dollar asset here, becomes something like the Calamari token, for example. Then you have the application of this previous example in blockchain on the Calamari network. So what we as Calamari network have to make sure is, because we are a blockchain, I took this little graphic here from a very great blog post from the founder of Polkadot. I would recommend, if you are interested in these sorts of systems by now, to have a look at that. It explains the forking and the resolution system that Polkadot chooses. We basically do three things in blockchain. One is when we have a fork, a disagreement in the system, which of those forks, which of those conflict resolutions do we choose? Which do we prefer over the other? Then the other one is the next one is a block valid? So all of the transactions, all of the things that happen inside of this block that lead to this fork, to this disagreement, are all of these individual contributors to that fork situation, are they valid? So validating a block is the second piece that needs consensus, and consensus here means everybody in the system has to agree that a block is valid. And then we get to the next part, which is who gets to produce the next block. And because thankfully, as Calamari and Manta Network, we run a parachain on Polkadot, we have the luxury of outsourcing the first two, which are the most critical pieces of consensus, because they give us economic security, security against people basically mining and proposing invalid blocks. We can outsource that to the Polkadot validators. So the only part that we as Manta Network have to take care of is decide who is going to be the next one to produce a block candidate. So this is a radically simpler system than the full problem, but in itself, the way I described it so far is also impossible, because as we've established earlier, when we make a consensus, we always have to basically create a what's the word? A resolution that satisfies a part of the participants, because in a disagreement we cannot satisfy all of them. So we will never have the situation that everybody in the network, in the blockchain, all nodes of the network agree on the outcome. Otherwise, if they do agree on the outcome, we didn't have a fork. We didn't have a disagreement in the first place. So getting everybody to agree is actually impossible. So what we need to do is we need to define a set of rules that is going to at least, and that's how blockchain does it, satisfy and like placate the majority or even a super majority of the network. So in some situations, there are different trade-offs to each of these, but suffice it to say that we will never be able to satisfy everybody. So now that we've gotten into this, is because we've outsourced to Polkadot and the first two pieces, let's have a look at what we've actually been building for Calamari Network here in the backend. As the next step, I wanted to here in this slide show a few desirable properties of a consensus, but I'll skip this one. This you can look this up in the video if interested. I've basically gone over most of the meaning of these earlier in the presentation. So looking at how block production on Calamari Network works at this point. So we are using there's a consensus implementation which is called Aura. Aura stands for authority round, and I actually had to look up why authority round abbreviates as Aura instead of Oro, as would make more sense. And the reason behind that is that the original implementation of authority round was created by the Ethereum Foundation, and it's actually being used at this point right now on the Coven test network. And they actually call it Oro. But then Parity came along, they forked the code, implemented it, made some changes, and are using it for Substrate now. And in order to distinguish it from the Ethereum Foundation version, they decided to just exchange the O with an A. Seems to be a more or less random choice in this case. So the way Aura works is that we have a set of 4 participants in this network in this case, and the algorithm is very simple. We just do round robin. So in sequence, whenever there is a slot to produce a block, on Calamari Network, a slot happens every 12 seconds. For us on the relay chain in Polkadot, for example, they have 6 seconds for each slot. And we have this very simple assignment of sequential assignment of block producers in this set. This comes with some challenges and problems. One of the problems is that, first of all, the block producer, when it's turn for producer number 2, for example, to produce a block, is known in advance because this algorithm is simple, right? And it repeats. So I always know what to I always know which node, which participant of the network will author a block at which time. So if I can make that block producer go offline, prevent them from communicating for a block, what that means is that in this 12-second time frame, that node 3 in this situation had time to produce a block. Because they couldn't, because they were offline for whatever reason, no block was produced. So we just skipped the thing. If we skip a block, that is not critical, but it is bad for throughput, because in this case, the way a blockchain works is we have a limited space in each block to put transactions in. And transactions typically aggregate from users wanting to transact, right? And so when there are more transactions than fit in a block, the transactions stay in a mempool and will be mined in the next block. Now, if that next block doesn't happen for 12 seconds, the transactions keep aggregating in the mempool, and instead of being put into a block, they will have to be mined at the next block, which is produced by number 4 in this case. And so this can cause a build-up, basically a pile-up of transactions in the mempool. As long as there are more transactions being submitted than can be put into a block at any time, that basically congests the network. And what that results in is it increases gas fees for everybody who wants to transact, and we won't be able to get as many transactions into the chain as we want to. So we want to avoid this scenario. So what we've been building over the last couple of weeks and months is, and that's started to be in the future. So our the first thing was to exchange. Okay, let me go into that in detail. So one of the things that we want to implement and are building on, that will be ready in the near future, is instead of having this simple algorithm that I was showing here of round robin assignment, we instead we have a verifiably random assignment of block producers. Verifiably random means the The lottery itself is hidden until after it has already happened. And after the lottery has happened, every participant on the network can verify after the fact that the person who claimed to be the winner of this lottery didn't actually cheat. So this VRF, it's called, is a primitive that's fairly well known by now, created in 2019. One of the first projects that started this and started using it because their founder came up with the idea was Algorand, for example. And this is now basically like open source usable, and we're going to adopt it for ourselves as well. So the main benefit of this a priori is that we have better censorship resistance, because now I cannot know which node is going to author the next block. So I don't know who to attack until it's already too late and they've produced their block candidate. So we increase resiliency against censorship in this case. But if a node that is part of the set of eligible candidates for the lottery is actually on offline by other reasons, not necessarily by being attacked, but for example, because the node runner just took it offline for some time, we are still going to lose the block because they are still eligible for the lottery, but because they're offline, they didn't produce a candidate, and nobody else can because it's they won the lottery, right? If they won the lottery, that means nobody else won the lottery, and that means that the slot will stay empty. So this is what's going to happen in the near future. This improvement of the chain, and that's going to pave the way for the next level of technology improvement on the block production side, and that is to on every time a session happens, when we decide who are the nodes that are eligible to produce blocks, we are actually checking whether a node is online or not. And only if the node is online, then we add it to the drawing of the lottery. So what this does is it removes people who are not running nodes from the set of eligibles. And so in this situation, you see that even though node 3 is offline, it has never been rolled in the lottery because it's not part of the eligible set. And so we've removed this this problem situation of dropping blocks when people go offline. There are some trade-offs and caveats to this because we cannot really do this on a block-by-block basis because unfortunately creating this staker set is quite computationally intensive. So we're going to have a more coarse staker set selection that isn't on every block, but rather we could say something like every 2 hours, or as a realistic example. These are this is just like a tentative thing. These are all parameters to be worked out. So every 2 hours we check who is online, and if somebody has gone offline in the meantime, we remove them from the set for the next session so that they don't continuously slow down the chain. And if they come back online 2 hours later, they will be re-added. So we have something like this planned that's going to happen after the previous improvements. So I think in the interest of time, I'm going to just skim over the ideas here of proof of work, because if you are in blockchain, chances are you've already heard of them. And if you're on this call, it's most likely that you've heard of them. So proof of work, most notably used by Bitcoin, has some very interesting properties. For example, it doesn't have to gate the set of stakers, and it's basically, if you want to think of it as a in relationship to what I was showing here earlier, proof of work is basically the same thing as this verifiably random lottery, with the exception that in here in our VRF, everybody only gets one drawing. You get one chance to be the winner. If you're not the winner, you can retry in the next slot 12 seconds later. If you don't impose this restriction, you let people roll and roll again and again until at some point they come up where they end up being the winner. You get proof of work, because then you have the fork choice rule be the first winner that we see, the winner with the smallest timestamp, is the one that is going to be the consensus, is going to be accepted as the valid next step. So interestingly, these are very closely related. The only difference is that here we're enforcing one vote, one chance per slot. With proof of work, we don't. The main takeaway here is we don't have to actually do this. It's needlessly wasteful because we have the security guarantee that proof of work imposes already done by Polkadot, and all we need to do is come up with a sequence of people who produce blocks. So we don't need the full set of proof of work. And people are moving away from proof of work. For whether it's right to do or not is up for decision. I'm not putting any my eggs in any basket here, but people are moving away from it because it's very computationally intensive, and that means energy intensive. So other ideas people came up with is proof of authority. That's what is currently running this selection of block producers. The idea here is that some authority that's outside of the system, that's not inside of the consensus laws, takes care of deciding who is eligible to produce blocks. In this case, for Calamari Network, that's Calamari governance. The problem with this is obviously it's a manual process, so somebody always has to accept new people into the set and remove people from the set if they misbehave. And so this doesn't scale. If there were 500 people, of which 100 are joining and leaving on a daily basis, you'd have 100 governance, 200 governance votes to do, and that's we'd either have to pay each of you a crazy amount in order to show up for those votes, or it's just not going to happen. So what we need to do is get away from this proof of authority model in order to get to a more automated way. And as Kenny has already introduced, we're moving to proof of stake. So the idea here is that instead of having the governance gate the set of nodes that are eligible, we're going to have everybody put their Calamari tokens as a backing of some collator candidate, we call them. So somebody who wants to run a node can elicit stake from other participants in the network, and he can also stake for his own collator. And if his stake is high enough in order to be eligible for, so it's one of the top, it's basically top ranked by top amount of stake on a collator. So the top X, let's say for example 30 or 50 nodes, the top 50 nodes that have the highest amount of stake on each of them are going to be the ones who are eligible to produce blocks. At this point, it becomes automated and a game of economics, because we need to incentivize people to run collators, we need to incentivize people to stake, and after that, market forces take over. That's the nice part, the nice thing of this about this solution. So all of y'all are going to get money for if you decide to stake on the network, if you decide to help ensuring that the collators that are the ones that are selected for validating blocks are the best ones. You're going to have an incentive in that, because the best collators are going to get the most rewards, of which you as a delegator are going to profit. So every participant has an incentive of making sure that their stake backs good candidates. So it becomes a self-balancing system, so to say. There's no consensus, no governance authority. Everybody collectively decide on who's going to produce blocks and who won't. So that's going to be kind of exciting to see, because it's also going to make the Calamari token usable, more usable than before. And it puts the onus on us or on the network altogether, that we have to make sure that the Calamari token is fairly decentralized. So if only a few people hold the most Calamari, it's going to become a plutocracy. That's an inherent danger with all proof of stake systems, and we need to and we are actually taking steps to decentralize ownership of Calamari to make sure that the system, as we're going to put it on chain. And by the way, we're not going to put anything on chain that you guys as Calamari governance are not going to vote for. So in the end, it's always your decision. The network is fully decentralized already. We as the project team don't control it. We're going to try to design this in a way that is going to make sure that this system works for all network participants and not just the few, not just the 1%, as some politicians like to say, for example. Okay, then that said, I'm almost done here, and I see we're already getting close to the hour. So I apologize for if we have to cut the Q&A a bit short. I'm happy to stay on longer. I just want to give you guys the roundabout of what it is we've been doing here and where we are standing. So we've already created preparatory changes. So if you run a collator, you might have noticed that's the session key migration that you have to do. Then Manta v330, which is now in the pipeline of being released, and we're actually going to start the on-chain vote today, later, for putting it on the network. That is the actual enablement of the consensus engine that's going to allow us to switch to VRF-based block production. And then staking is scheduled for Q3, and it's almost around the corner. So the very next release after the one that we're starting to enact today, the very next release is going to come with on-chain staking enabled. It's not necessarily going to be fully integrated into the Calamari or the next application, but you're going to be able to use it through Polkadot.js in order to put your stake behind collators and register your collator there. So that's exciting. We're going to get staking soon, and then in the future I will update this and make it even more resilient with the previously called block production by VRF. So let me close with one interesting little parallel, because we basically are the little brother of Ethereum in this situation, with Calamari scheduled to merge in this quarter, almost at the same time as Ethereum, as our big brother here is scheduling a merge. And unlike Ethereum, who are transitioning from proof of work to proof of stake, we are transitioning from proof of authority to proof of stake. But the underlying mechanisms and methods, and the fact that we have to take precautions that our new chain that listens to the new consensus rules and staking is still compatible with the whole history of blocks that the Calamari network has had up to today, so that we don't have to relaunch the network, because obviously I don't think anybody would want that. So the procedure that Ethereum is doing and that we are doing here for Calamari network is very, very similar. It's with the little brother, because there's obviously ETH is at this point much larger, but I think it's interesting to point out the parallel that we're basically doing the same thing. Okay, that said, finally, with a few minutes to spare, let's get to the Q&A. And with that, I'll give back to you, Kenny, I guess, for moderation.
Sure. Yeah. So in terms of time, I think we'll just have one question because we're already a little bit over. And this is from Marco. What are some of the major challenges you've been grasping with the transition from POA to POS?
The one very major challenge is the one that I was just alluding to, that Ethereum is also facing, and that is we want to enable proof of stake without losing the history of the chain, without breaking compatibility with how it used to run. the fact that Ethereum is taking multiple years to come up with a solution for them, which is also due to testing, is basically evidencing the fact that this is a difficult problem. We're standing on the shoulders of giants, getting inspired by both Ethereum and Moonbeam, who are doing something similar. And thanks to the spirit of open source, we get to profit a lot from what other projects are doing in this change. But the one major problematic scenario is on the development side to make this transition seamless in a way that we're not disrupting network operations. And the other main challenge is on the incentivization side. So as I was saying in proof of stake consensus, we have to incentivize participants to do the right thing. And designing those incentives is also a tricky topic that is under active research, like all over the blockchain space. And we've been putting quite some thought into over the last few months as well. Where actually, by the way, we're not going to impose any of our designs on you. Again, the final word will be with the Calamari community, and this will also, whatever we came up with, will also be up for discussion with all of you to make sure that we're aligning with the community.
Awesome. All right. Well, thank you, Adam. That was a great presentation, and I learned a lot with the examples, and I think the audience kind of appreciated those examples as well. Very, very relatable. But thank you, everyone.
Hopefully not too relatable. I hope nobody got held at gunpoint at this time.
Yeah, I hope this trend of gun violence in the U.S. doesn't continue this way. So. But yeah, thank you everyone for joining. And this is our first talk of a series of Manta Tech Talks. Thank you, Adam, for joining and walking us through the consensus level stuff. And yeah, we'll see you guys next week to talk about zero knowledge proofs. All right.
All right. Thanks, everyone.